In lesson 11.3, we're going to start talking a little bit about this idea of a normal distribution. All right, so to start off with some vocab, first of all, normal distribution. Okay, normal distribution is a probability distribution modeled by a bell-shaped curve that is symmetric about the mean. All right, we did frequency tables back in the last chapter, back in chapter 10. So we spent some time talking about frequency tables, and those were things where we had the probability bars. And those probability bars look something like this. And so the curve, we said this was symmetric, all right, because it had this shape right in the middle. Well, if the data is not based on only having discrete outcomes like 0, 1, 2, 3, and 4, but instead we can have the data on a continuous level, values in between like decimal values. Well, now your data is going to be spread out among this smooth curve, which we refer to as the bell curve. All right? The normal curve is, again, that bell-shaped curve that models a normal distribution. And again, we're now talking about a continuous set of data, no longer looking at discrete data values and probability bars for a histogram. Okay? The standard normal distribution is a normal distribution that has a mean of 0 and a standard deviation of 1. Now, we can normalize a set of data by using something called a z-score. And all of this may seem completely, off task right now, like you have no idea what we're talking about, but eventually we'll get into this idea. We can normalize our data, and then we can use a z-score for a particular x value. All right? We only have ways to measure percentages down below. In this very next part, we're going to talk about areas under a normal curve. We only have a way to talk about those areas that are within 1 standard deviation, 2 standard deviations, or whatever. But if we normalize the curve by using a z-score, then we can actually use that information to help us find specific probabilities for specific values of x. And so to normalize that, again, we use something called a z-score, which you'll understand more as we get down to it down below. All right? So let's just continue with this. The normal distribution with a mean of x bar and a standard deviation of sigma has the following properties. First of all, the total area under the related normal curve is 1. So all of the data, every single thing, if the data is normally distributed, the total area under it is a probability of 1. All right? About 68% of the area lies within 1 standard deviation of the mean. So this says x bar minus sigma. This is 1 standard deviation below the mean. This is x bar plus sigma, so that's 1 standard deviation above the mean. Now, 68% of the data will fit in that area there. All right? If we go out within 2 standard deviations of x bar, now 95% of the data is within 2 standard deviations. And 99.7% of the data is within 3 standard deviations. All right? Outside of 3 standard deviations, the data that's out here and out here is less than 0.3% of the data. All right? Those would be the outlier data points, and those are definitely outside of our normal distribution. Okay? All right. Now, if we want to break that down further then, if I take my 68% and I split it in half, okay, 34% of the data will be within 1 standard deviation below, and 34% of the data will be within 34% of the mean above. All right? Now, the makeup there ends up being 27%, okay, because 68% plus 27% gives me my 95%, right? So if I split that 27 up in half, then 13.5% is within 2 standard deviations, all right? So the amount of data between 1 standard deviation above and 2 standard deviations above is 13.5% of my data, all right? Same thing on the other side. 1 standard deviation below to 2 standard deviations below is 13.5% of the data, all right? From there, we've got about 2.7% of the data left to fill in there. All right, and so 2.35% of the data then, 4.7% of the data. So 4.7 divided by 2 tells me that 2.35% of the data lies between 3 and 2, well, I'll say between 2 and 3 standard deviations, and the same thing over here. And as I told you before, less than 3% of the data goes outside of 3 standard deviations. So if I split that in half, that means that I get 0.15% of the data there and 0.15% of the data there. Altogether, if you added all this up, this would be 100% of the data. All right? Okay, so let's go ahead and see if we can't use that to find a normal probability. All right? It says a normal distribution has a mean of x bar and a standard deviation of sigma. For a randomly selected value from, for a randomly selected value x from the distribution, find the probability that x bar will be less than or equal to x, which will be less than or equal to x bar plus 3 standard deviations, or 3 sigma. So what we're saying is that we want to know what's the probability that an x value will be somewhere between x bar and x bar plus 3 sigma. Well, x bar plus 3 sigma says 3 standard deviations above the mean, and obviously we want to know what's the probability that that data point is going to be in this region here. All right? So the probability that that value for x is going to be within 1 standard deviation, if you look at that chart at the bottom of the previous page, that's going to be 34%. Okay, so the probability the randomly selected value, x value, lies between x bar and x bar plus 3 sigma, and all we're saying here is between the mean and 3 standard deviations above. Okay, that would be that shaded area under the normal curve. So we're going to break that up into chunks. The probability that's in this area right here, we know is 34%. The probability that it's in, I'll change pen colors here, the probability that it's in this color right here, in this area right here, okay, that's another 13.5%. All right? And then the probability that it's in this region over here, we said, according to our chart, was 2.35%. So if I add all of those percentages together, I get 49.85%, or 0.4985, whichever one you want to put. Now, if we're talking about a probability, you can leave it as a decimal, or you can change it to a percent. There's a 49.85% chance that that value for x is going to be in that region right there. All right? So you guys try the checkpoint problem down below, and we'll be right back with a solution. All right, a normal distribution has a mean of x bar and a standard deviation of sigma. Find the probability that the randomly selected value x will be somewhere less than or equal to x bar minus sigma. Okay, x bar minus sigma is 1 standard deviation below. So I'm going to use this to say, look, that's where I want to be, and I want x to be somewhere less than that. So that would be this over here, right? Now, according to my chart from the previous page, I know that the area of this segment, or this section rather, all right, and we'll just go right here, between 2 and 3 standard between 1 and 2 standard deviations below, we said that that area right there is 0.135. We're going to put them as probabilities this time instead of percents, but it doesn't really matter. The probability that it's between 3 and 2 standard deviations below is 0.0235, because that's the same as 2.35%. And the probability that it's over here in this little skinny region over here, more than 3 standard deviations below, becomes 0.0015, because again, 0.15% is the same thing as 0.0015. So then I would add all of those things together, and it would tell me that the probability that x will be less than or equal to 1 standard deviation below is going to be 0.16. All right? All right, so now let's take a look at some normally distributed data. All right, now we're going to look at a data set that we are going to assume is normally distributed. And again, the math scores from a 2004 SAT exam are normally distributed. That means that they follow the rules for a normal distribution. It says the mean is 518, so the mean is now no longer this normal distribution. All right, a normal distribution had x bar is equal to 0, and then we could kind of work from there. Now all of a sudden x bar is actually a number, it's 518. The standard deviation of the data set is 114, so that means that if I add 114 to 518, I get 632. So this becomes x bar plus sigma. All right? this right here would be x bar plus 2 sigma. And this out here would be x bar plus 3 sigma. All right, and so all I do is I just add 114 to 518 and get the 632, and then add it again and get the 746, and then add it again and get the 860. Well, to go the other way, one standard deviation below, this would be x bar minus sigma. Okay, this one right here would be x bar minus 2 sigma, and this one right here would be x bar minus 3 sigma. All right, so this is 3 standard deviations below. This is 176. This is 2 standard deviations below. This is 2 standard deviations below. This is 1 below. This is 3 below. So anyway, we just add our standard deviation or subtract it from our mean to get those points at the various standard deviations. Okay. All right. About what percent of test takers have scored between a 518 and a 746? Well, 518 is the mean, is x bar. That's our mean. And 746 happens to be exactly 2 standard deviations above the mean. All right? Well, the scores from 518 to 736 represent 2 standard deviations to the right of the mean. Now, it doesn't really matter if it's right or left because it's the same amount of area. So the percent of test takers that scored between a 518 and 746 becomes 34% for the first standard deviation, and between the first and second standard deviation is 13.5%. So I add all of those up and it's 47.5%, or you can have it as 0.475. But percentage labels were given, so we're just going to use percents. Okay. All right, about what percent of the test takers have scored less than a 404? All right, so let's clear all this out of here. Okay, less than a 404 now. Okay, a 404 is right here. That is 1 standard deviation below. All right, so I want basically the area between 1 and 2 standard deviations, the area from 2 to 3 standard deviations, and the area from 3 standard deviations and below. Well, all you have to do is look back at the previous example up here. Look at the checkpoint problem that you just did. The checkpoint problem that you just did says, what's the probability that x is less than 1 standard deviation below the mean? Well, that's exactly what this area is right here. So I ought to get 0.16. But again, if you want to plug all those back in, again, this happens to be 1 standard deviation to the left of the mean, and then everything to the left of that. So the percentage that is 404 and less becomes 13.5%, 2.35%, and 0.15%. And so this actually ends up being 16%, not 0.16, but it's the same thing. All right? All right, let's take a look at a height survey. We have a survey of a group of women, and we find out that the height of this group of women is normally distributed with a mean of 64.5 inches. Now, 64.5 inches, 60 inches is exactly 5 foot, and so this would be 5 foot 4.5 would be the average height of a group of women. Okay? Standard deviation is 2.5 inches. Find the probability that a woman is at most 58 inches tall. All right? So the first thing we have to do is we have to figure out what is our bell curve going to look like. All right? We know that we're going to have our little bell curve here, and we know that x bar is going to be 64.5. All right? Now, 1 standard deviation above that is going to be 64.5 plus 2.5. Okay, and 64.5 plus 2.5 comes out to 67 here. All right, so 67 inches would be 1 standard deviation above. All right, 2 standard deviations above would be 69.5, and 3 standard deviations above would be at 70. Okay, then we're going to go the other way. 1 standard deviation below would be at 62. All right. 2 standard deviations below would be at 59.5, and 3 standard deviations below would be at 57 inches. All right? So that's what our normal curve is going to look like based on those values from our standard deviation. Well, here's the issue. I want to know what is the probability that a woman is less than or equal to 58 inches tall. Now, 58 inches tall, well, that's somewhere in this neighborhood right here, right? And I can't just get the area under the curve because it's not right on one of my standard deviations. So what I'm going to do is I'm going to normalize my data by taking a z-score. Okay? The value that I'm looking for is x, 58 inches. All right? So we have 58 minus the average, x bar, which is 64.5, and we're going to divide that by sigma, which is our standard deviation, which is 2.5. Okay? When I plug all that in, I get a standard deviation, a z-score of negative 2.6. All right. Now, this standard normal table is on page 759 in your textbook. Okay? You will have access to this standard normal table. You are not required to memorize this chart. Okay? Now, unfortunately, I'm going to have to scroll down to get this value. You guys should be able to see it, but I'll help you out a little bit with it because I'm kind of out of room on my screen here. But it says the probability that x is less than or equal to 58 becomes the probability that the z-score is less than or equal to negative 2.6. All right? And so all we then have to do is scroll down here, and we're going to take a look then at our data. Okay? Now, again, I had to move that, so it's going to be a little hard to read up above. But negative 2.6 right here tells me that probability is 0.0047. 0.0047. All right? So then, what I have to do, see if I can get that back in the same spot. Pretty close. The table shows that the probability that z is less than or equal to negative 2.6 is 0.0047. So the probability that a woman is at most 58 inches tall, that means she's 58 inches or shorter, is approximately 0.47% or 0.0047. All right, now what is 58 inches? Well, 58 inches would be 2 inches short of 5 foot. So that would be 4 foot 10 inches. And as you can imagine, there's not a lot of people that are less than 4 foot 10. All right, if you are, sorry, I'm not picking on you. Okay? All right, so let's try the checkpoint problem down below. You got 2 checkpoint problems to try. We're going to be using our standard normal table for number 3, and you should just be able to look at that previous data on the previous page for example number 2. So try those 2 checkpoint problems. You may have to refer back to page 293 in your text to do that. Okay? Or 293 in your note-taking guide. All right, what percent of test takers receive a score of between 404 and 632? Well, 404 is 1 standard deviation below, okay, or x bar minus sigma. 632 is x bar plus sigma. Okay, so it's 1 standard deviation above the mean. This is 1 standard deviation below. So if you remember from the first page here, we said if this is my mean, 1 standard deviation above and below, 68% of the data is between 1 standard deviation above and below. And so that's exactly where a 404 and 632 are. And so 68% of the people scored between a 404 and a 632. All right? Find the probability that a woman is at most 70 inches tall. So that says we want to find the probability that she is no more than 70 inches tall. The probability that x is less than or equal to 70 then becomes the probability that z, the z-score, is less than or equal to what? Well, we have to calculate the z-score first. And if you recall, the z-score is calculated very easily by taking the x value minus x bar and dividing by the standard deviation. So the x value I want is 70, minus the average, or the x bar, which is 64.5, and divide that by the standard deviation of 2.5. That tells us our z-score that represents 70 inches is 2.2. So I want to find out what's the probability that the z-score is less than or equal to 2.2. Now, you can look up above on your standard normal table. You're going to be looking on the top piece of that chart, or on page 759 in your text. And it says when z is equal to 2, and I can't quite get to it here, so I'll have to kind of scroll here, and you guys can see it up above. All right? The z-score becomes 2.2. So right here is 2.2, and that says that the probability that the z-score is less than 2.2, which is also the probability that the height is less than or equal to 70 inches, is 0.9861. All right? So let's go back down here. All right, this becomes 0.9861. Now, as a percent, that's 98.61% of women that were surveyed for this particular normal distribution are less than or equal to 70 inches tall. all right? And 70 inches tall is exactly 5 foot 10 inches. So what we're saying is that 98.6% of the population of women is going to be less than or equal to 5 foot 10. Another way to look at that is less than 2% of the population is more than 5'10". Okay? Now, this data may potentially be a little bit outdated, but that's what the standard normal table tells us, and so that's what we're going to work with for that.